Alrighty, we are back. This is Calculus 1. We're looking at practice test for chapter 1 and 2. So this is the review. Some of these problems will definitely be on the test, but the test won't look exactly like this. So we're going to take a look at chapter 1 and 2. Let's jump right in here. It says to graph this negative x squared plus 2 when x is greater than or equal to 0. So that's that half. And x plus 2 when x is less than 0. So that's that half. So this is linear. It starts at 2. And then we would go up 2, or up 1 and over 1. Up 1 and over 1. Sorry, the slope is 1. And the starting point, right, is 2. So graphing a line just like so. You don't want to do that in pencil. I should have probably said that because this is only for the lower half. So we could have also went down 1 and over 1 and down 1 and over 1. So this part we're going to erase. And that's actually an open circle right there, because it doesn't include 0. So it's just when x is less than 0. So this part of the graph is right there. Negative x squared plus 2 when x is greater than 0. So negative, it flips it over the x-axis. X squared means it's a parabola, right? The parent graph looks like this. Just a parabola that opens up. That's y equals x squared. But they threw a negative on it and a plus 2, so that plus 2 moved it up 2 spots, and the negative reflects it over the x-axis. And it's only this half of it, so just a parabola going this way. So there's my sketch, and now actually we do fill in that dot because that is part of the parabola. All right. So now they have questions. H of 0. So when it's 0, we would use this. So negative 0 squared plus 2. The opposite of 0 squared, not negative. And so that's just 2. We could have also said, oh, gee, look, x is 0. What's y? It's 2. So we could have pulled it off the graph. H of negative 2. When it's negative 2, we would use this. And again, we could look off of our graph. That's going to be 0, but we could also put it into there and do it algebraically. Either way, we got the graph right there. H of 4, I didn't really graph it, so I'd use that. 4 squared, so the opposite of 4 squared plus 2, that is negative 16 plus 2, that is negative 14. So that's going to be way down here if you go out to 4. And then they want us to check the limit as x approaches 0. So we could do this off of the graph. That is, as I'm going from the left side, we're approaching 2. If I'm going from the right hand, it also approaches 2. So they have a continuous graph there. So that's going to be 2. The limit as x approaches 0 of h of x. All right, so that's pretty quick. Let's take a look at number 2. And there's a bunch of A, B, C, D, E, F, G here. Let's see if we can squeeze it in here. F of x is equal to x plus 1. G of x is equal to 1 over x plus 2. And h of x is equal to e to the x. And again, remember on the test, you can just use a scientific calculator, not a graphing calculator. So just scientific. So, you should know basic graphs, how to sketch a graph of a parabola and how to sketch a graph of a linear equation. All right, so here we go. What are we doing? The domain of g of x and f of x. So domain of f of x So that is remember the restrictions, you can't divide by 0. So we just have to worry about the denominator being 0. And so x equals -1 would be, you can't have that. -1 gets you 0 on the bottom. So when we talk about the domain, that would be -infinity to -1, not inclusive. You would use parentheses, not brackets. A bracket means it includes it. A parenthesis means it excludes it, in union with -1 to infinity. So everything else is okay for the domain, but not -1. The domain for g of x, that is going to be just about the same thing, right? It's just x plus 2 equals 0, so -2 is out. So it's going to look very, very, very much the same as f of x. And they're not worried about h of x. If they would have asked for h of x, that would have been all reals. You can put any x in for that, positive or negative. So that would have been -infinity to infinity. All right. So now find f of g of x, find g of f of x, find h of 0, and find h of g of x. Okay, so C and D are going to take a little, they're going to be a little more involved. B, find f of 1. Here, we could do that quick. F of 1 is easy peasy. So that just means we pop a 1 in anywhere where there's an x. And we simplify it. Piece of cake, 1/2. Let's jump to E and F, and then I'll erase the board mostly, and then we'll do the f of g of x and all that. So let's jump down to E and F. So E is just find h of 0, which is just put a 0 in there, which is easy, right? 0 to any power, anything to the 0 power rather, is 1. And so even on your scientific calculator, you have an E button, the second ln, and you could put it to the 0 power, but it's kind of a waste of time. And then find h of g of x. That's also pretty easy in the context of these problems, because you're just taking this and putting it in for x. So that's just going to be e to the 1 over x plus 2 power. That's all. So there's nothing to simplify or anything there. All right. I'm going to get rid of number 1 here, and then we'll do the B or C and D. So let's take a look at those. Those are a little more complicated. So C, they want f of g of x. So what does that mean? That means you're going to substitute g of x, this, we're going to substitute in for the x's. So f of g of x is going to be 1 over x plus 2 over 1 over x plus 2 plus 1. So basically, I just replace this x and this x with that. Now, we can't leave it like that, so let's fix it. That's a compound fraction. They got a fraction over a fraction. We don't like those. So what we'll do is the LCD for the numerator and the denominator is x plus 2. So we will multiply both top and bottom, both numerator and denominator, by x plus 2. And we'll kind of do the distributive property there. Here, it's going to look like this. X plus 2 over x plus 2 over x plus 2 over x plus 2 plus x plus 2. So I kind of did the distributive property. You know, I multiplied it by that and multiplied it by that, there and there. That's just a 1, that's just a 1. So we end up with 1 over 1 plus x plus 2, which is x plus 3. So it's simplified down pretty nicely. All right, g of f of x. Let's go the other way around. So g of f of x is going to look like this. So we're going to take this guy, x over x plus 1, and we're going to jam it in right there. So there's only one spot to substitute. Plus 2. And now we can't leave it like that. We can't have a fraction over a fraction. So the LCD is going to just be x plus 1. So we're going to take this times x plus 1 and this times x plus 1. On the top, I get x plus 1. In the denominator, I do the distributive property. I get x plus 1 over x plus 1 plus 2 times x plus 1. And then again, if I simplify, this is 1 plus 2x plus 2. And so I end up with x plus 1 in the numerator and 2x plus 3 in the denominator. 2x plus 3? Hold on, what do I have there? 2x plus 2. Oh, wait. I left out an x. So little quick fix here. I did this too quickly. I did it there and did the distributive property. That was fine. But here, oh no, I'm supposed to have an x times x plus 1 up there, which means when those x plus 1s cancel, I don't get 1. I get 1x. And so 1x plus 2x plus 2 is 3x plus 2. Oops, don't forget that. Don't forget the x. See, haste makes mistakes. All right. So this is, again, we're on page 33 of the note packet from chapter 3. So now let's get rid of this. And continue on here. We got 3a is find the limit as x approaches -4 of x squared plus x minus 12 over x plus 4. Now, again, there's a couple of ways we can find limits. Sometimes it's just as easy as substituting it in, but if we substitute it in right now, we have -4 plus 4, that's 0 on the bottom. That's bad. So we can do this problem, but what we're going to do is we are going to factor it. So multiplies to be -12, adds up to be +1. That's x plus 4, x minus 3 over x plus 4. And so when we factor it, it still has the limit on it. All right, now the x plus 4's cancel. And so we're left with this, the limit as x approaches -4 of just x minus 3. And now you can just substitute in the -4. -4 minus 3 is -7. And so that's what that will be approaching, is -7. Let's take a look at B. That one was interesting. The limit as x approaches 1. But then they have 1 minus the square root of x in the numerator and 1 minus x in the denominator. And this is one of those places where we're going to use the conjugate, but we're actually going to rationalize the numerator. I know in pre-calc you were really used to rationalizing the denominator, and maybe depending on how new your pre-calc class was, you did rationalize the numerator sometimes. But we're going to do the numerator here. We're going to multiply by the conjugate, numerator and denominator, and don't multiply it out. Don't multiply it out on the bottom, just the top. So let's fix the top. So the top is 1 plus the square root of x minus the square root of x minus x, right? Because the square root of x times the square root of x is just x. And then the bottom, we're going to leave it just like this. And you'll see what's happening here in a second. We still have the limit as x approaches 1. We still have the limit as x approaches 1. But now this cancels out, and we just have 1 minus x in the numerator. Well, 1 minus x in the numerator, 1 minus x in the denominator. We end up with 1 over 1 plus the square root of x. And now we can do that substitution. And so the limit as x approaches 1 is 1/2. All right, here I'm going to squeak c in over here. C is easy peasy. So c doesn't have any, nothing in the denominator to worry about. It's just as x approaches 3 of a continuous function where there isn't discontinuity. So really all you're doing there is with this limit, you just pop in a 3 everywhere we substitute in the 3. And then 9 times 4 plus 9 minus 4, that shakes out to be 41. So C was relatively easy. D, not that easy. I'm going to take a look at D right now because we're going to have to use a little bit of our memorizing techniques here. All right, so far so good. Limits. And let's look at D is the limit as x approaches 2, that's not a big deal, of the sine of pi x over 2. So basically, again, we can sub it in. There's nothing in the denominator. It's in the numerator, so it's continuous. But what we're looking at there then, if we sub it in, is the sine of 2 pi over 2. And so now you have to remember what the sine of 2 pi is. And that's going to be a quadrantal angle, right? Remember our unit circle like this, going around a little unit circle. So we got 1 comma 0, we got 0 comma negative 1, we got negative 1 comma 0, and we got 0 comma negative 1. And then remember coleslaw, CS, 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 CS. And so this is 0 or 2 pi. And then this would be pi over 2, and this would be pi, and this would be 3 pi over 2. Right? And if we had degrees on there, right, that's 90 degrees, that's 180 degrees, that's 270 degrees, and that's 360 degrees, if we were worried about degrees. So that's a way to memorize the quadrantal angles. You could also have this memorized with the sine curve. The sine curve is pretty easy. And so is the cosine curve. And so that's another way to do it is, 180 we're 0, 360 we're 0, and 0 we're 0. And on cosine, 180 is negative 1, and then this one's 90, and this one's 270. And that's 360. And so that's another way of remembering it, is just doing the basic sine and cosine curve. This way I think is a little faster. So that's usually how we demo it in calc. All right, so anyway, all of that work to find out that the sine is 0. And so we got 0 over 2, which is fine. That exists. It's 0. So the limit as x approaches 2 is 0 on that one. Let's look at E. E is just a simple factoring one. So the limit as x approaches 5 And yeah, they might have 5 from the right hand side, which it's not going to matter here because it's a defined limit. So we factor the bottom, x plus 5, x minus 5, and then get rid of the x minus 5s. So when we simplify it, factor and simplify, now there's no longer a problem. It was a problem if we just put 5 in there. 5 squared is 25, 25 minus 25 is 0. But after we factor it and simplify it, now it's not a problem. It's 1 over 5 plus 5, which is 1/10. So the limit as x approaches 5 is 1/10. That one, the cotangent of x. That one is going to be a little bit of a problem. We're going to have to take a look at that one to see what's happening there. The other ones aren't that bad, but that one we're going to need to know some stuff here. And so for this one, we're going to need, remember, quick mnemonic, 30 degrees, 45 degrees, and 60 degrees. And then remember that's pi over 6, that's pi over 4, and this is pi over 3. So you can make this little chart right on your test, right when you get your test, you can write this down on your scrap. And sine and cosine. And so this is the easiest way. This is the easiest way I've ever seen this done out. So it's 1, 2, 3, 3, 2, 1. And then you divide everything by 2. And then you throw a square root in the numerator, just the numerator of everything. And so this is the square root of 1 is just 1. So that's just going to stay 1/2. But that's the square root of 2 over 2. That's the square root of 3 over 2. That's the square root of 3 over 2. That's the square root of 2 over 2. And so now the sine of 45 degrees, square root of 2 over 2. The cosine of 45 degrees, square root of 2 over 2. The sine of 30 degrees, or pi over 6, is 1/2. This is first quadrant, of course. The cosine of 30 degrees, square root of 3 over 2. The sine of 60 degrees, or pi over 3, is the square root of 3 over 2. And the cosine of pi over 3 is 1/2. And so it's a nice little chart. It's really quick. You get that written down right away. And then you don't have to have that just pulling out of your memory when you're trying to work a problem. So then when you come across a problem like the limit as x approaches pi of the cotangent of x, and now we can rewrite it as cosine x over sine x. And as you're approaching pi, that's, if you take a look at what's going on here at pi, what is happening at pi, it's approaching it. And we got sine on the bottom, so that's 0. So this is like -1 over 0, which is not cool if we actually just subbed in pi. So we can't do that. That's an asymptote. And so what we're going to have to do is we're going to have to look at the left-hand limit and the right-hand limit and see if they're both going to either positive infinity or both going to negative infinity. All right, and so let's do that. So we're going to look at the limit as x approaches pi from the left side of cosine x over sine x. And so we know it's infinity, but now the question is it positive over positive? Is it negative over negative, or is it positive over negative? So what's happening with cosine as we approach it from the left. And so this might be easier with the actual cosine graph. If we take a look at that. And so pi is right here. And so as we're approaching from the left of the graph, we're coming from the left side, it's negative, right? And as we're approaching sine from the left side, that's going to be positive. And we could do it like this also. You could think of it like coming from this way. The cosine is negative. If we do all-star trig class, all-star trig class. So as I'm coming from this way, sine is going to be positive, cosine is going to be negative. And so that means that's going to negative infinity. Again, if we looked at the sine curve, from the positive side, from the left, it's positive. All right? So that's negative infinity. The limit as x approaches pi from the right-hand side of cosine of x over sine of x. So now we're approaching it from here, from coming up from down here. So this time, the cosine is going to be negative, but so is the sine. The only thing that's positive in the third quadrant is tangent. So as I'm coming from this side, tangent's the only positive one. So that is negative for sine and negative for cosine. And so that means that this negative infinity does not match this positive infinity. So the limit as x approaches pi of the cotangent of x does not exist. Because the right and the left hand limits are different. All right. Okay, so let's look at G. So for G, we're going to need what's going on here? The limit as x approaches 0 of 1 plus 1 over x squared. So again, we could split this up and say the limit as x approaches 0 of a constant, that's just the constant, and then the limit as x approaches 0 of 1 over x squared. That one, again, we're going to have to look at the right and the left-hand limit here to see if they are the same. So this is just one. But this, we're going to have to kind of split into two problems. So we're going to do the limit as x approaches 0 from the left side of 1 over x squared, and the limit as x approaches 0 from the right side of 1 over x squared. And so again, there's an asymptote there. That's an asymptote. So we're looking at infinity, but is it positive infinity or negative infinity? And so from the left side, what's going on with that? As it's approaching 0 from the left. Well, the top is 1, so that's just positive no matter what. That's going to be positive no matter what, because that's 1, and that's 1. But for x squared, so we're looking at a negative from the left side of 0. So left side of 0, that would be like negative 0.0001. What negative 0.00001? Well, here's the deal. If I put in a negative value, negative 0.1, and then square it, it's positive. And so that's positive over positive. So that's going to positive infinity. The 1 is positive. From the positive side, 0.1 squared is positive. 0.01 squared is positive. That's going to be positive also. And so that approaches infinity. So at the end of the day, when we work that back in, these match from the left-hand side and the right-hand side limits. And so that is the defined limit. Then the limit as it approaches 0 is infinity. And infinity plus 1, that sounds like two little kids arguing, right? on the playground. That is our limit. So the limit as x approaches 0 of 1 plus 1 over x squared is infinity. All right. So we could just factor and cancel that one too. That's another factor and cancel one. So that's pretty quick. Okay, voila. Okay. So with these limit problems, you should have seen patterns that, you know, sometimes we factor and get rid of things. Sometimes we have to look at left and right hand limits and see if they're the same. So again, they had this one coming from the left-hand side, I think. I think there's a tiny little negative right there. But again, that's not going to matter because it's defined. You can factor here. So I factor the numerator, multiplies to be -3, adds up to be +2. That's +3 and -1. Multiplies to be -6, but adds up to +1. That's +3 and -2. And so when we factor it, this was h, 3h. We can cancel the x plus 3's. And then you can just pop in the 3. So 3 minus 1 over 3 minus 2. That is 2 over 1. Which is 2. So there's our limit. The limit as x approaches 3 from the left or from the right. It's going to be defined as the same thing. There will just be a hole there, which is removable discontinuity. Remember that. All right. So what are we doing? Given this function, find all discontinuities by factoring the numerator and denominator, then state if they are removable or non-removable, then draw them on a graph, draw the hole, or a dash line to show the appropriate discontinuities on the graph to the right, and then they want the limit as x approaches -2 of f of x, and the limit as x approaches +2 of f of x. Okay, so let's do that. On my printout, it actually kind of spilled over to the next page. On yours, it might not. So we're kind of 33, 34. Mine, it's split. Yours might all be still on 33, number 4. F of x is equal to x squared minus x minus 2 over x squared minus 4. So again, you got to have that factoring down. Multiplies to be -2, adds up to be -1. That is -2 and 1. And difference of two perfect squares, x minus 2, x plus 2. And we cancel the x minus 2's. And so now we're looking at this for our function. We have x plus 1 over x plus 2. So when we graph this, there is going to be infinite discontinuity. There is a vertical asymptote at -2. All right. There will be a hole at +2. And so these graphs, this is just going to be a sketch. I mean, you could actually find some points if you wanted to. I'm just sketching it. Does it go through at, well, it does go through at 1. So you could do, or -1 is definitely a point. So get that point on the graph. Something like that. And then at +2, because we canceled those, there's discontinuity there. That is removable, but there's a hole right there. All right. And then the other side of it is going to look like Again, this is just a sketch, but it's going to be going like that. All right. Again, in pre-calculus, you should have probably looked at like horizontal asymptotes and vertical asymptotes. We're not interested in those right now. We're just looking at the discontinuity. So there's infinite discontinuity here at -2. That's infinite discontinuity. And this is removable discontinuity here. That is a hole. All right. And so when we look at this, they have the limit as x approaches -2 of f of x. Okay, well, this way it's going to positive infinity. This way it's going to negative infinity. So they don't match. That does not exist. Now again, if you wanted to do that algebraically, we could take a look at that. But since we have the graph right there, the idea is to not do it algebraically and just say, look, this one was positive infinity, and coming from the right was negative infinity. It was going down forever. So as I approach, it goes down to negative infinity. As I approach, it goes up and up and up forever. So positive infinity and negative infinity, those don't match. So that's why it does not exist. If I was looking at it, we could go back up to here. And do the little plus over minus thing, you know what I mean? So I could put in things just to the left of -2, so -1.9, we'll say. And so -1.9, that would be negative on the top, and that would be positive on the bottom, so that'd be negative overall. And, you know, you could take a look at what's happening with the numerator and the denominator to see what's going on with it. We'd have to go all the way back up here, though. We'd want that in there. So, but you have a graph, so use the graph for that one. And then C, they're like, okay, well, what about the limit as it approaches +2 of f of x? And again, after we had factored and canceled, you can put the +2 in if you wanted to do it algebraically. And it approaches 3/4. You probably can't get that off the graph. It's just a sketch. So my sketch is not very good because that would have to be 1 all the way up there. All right. So we have infinite discontinuity with a vertical asymptote. That's non-removable. And removable discontinuity with that, that's a hole. When you get something to cancel like that, that creates a hole in the graph. All right. Okay, let's jump to number 5. You had to do a whole bunch of problems like number 5 on the homework. They threw a lot of those at you. So number 5 is kind of filling this chart here. They want us to do it numerically as x approaches 0. F of x equals x over x plus 1 minus 1. So yeah, on the XYZ homework, you had to do these a bunch. So we got x and y, and they want here, we'll and we're closing in on 0. So from the left, that's like negative 0.01, negative 0.001, negative 0.0001. And then from the right, that's like 0.01 and 0.001 and 0.0001. And then you sub those in. So you're doing this in your calculator, you're putting that in there, figuring it out, and it's spitting out 1.9949, 1.9995, 1.99995. And then going from here, it's 2.000, or 2 zeros and a 4, 9, 9. And then 2.0005, and then 2.00005. And so you can kind of see, right, what's happening here. What is this getting ever close to? What is that getting ever close to? That is obviously approaching 2. All right, so we did it numerically. Find the vertical asymptote, if any, of the graphs of the following functions. So again, number 6, that's just a gimme. That one is no work at all. They already have it factored for us. And so there's a vertical asymptote at x equals 2. So vertical asymptote at x equals 2, that's what would zero it out. The graph then would look like that, you know, there'd be 2 and it'd just be a big old vertical line there with the graph going on the other sides. B, g of x is equal to x minus 1 over x squared plus 7x minus 8. So they want you to flex your algebra muscles. Factor multiplies to be negative 8, adds up to be positive 7. That's got to be plus 8 minus 1. And then those minus 1s are going to cancel. And so we end up with 1 over x plus 8. Now, again, they're only interested in asymptotes, vertical asymptotes. So there is a vertical asymptote at x equals negative 8. There is a hole at x equals 1, but they didn't ask for any discontinuities. They just want the infinite discontinuities. So on to number 7. Find the following limits for f of x equals 2 plus x over 1 minus x. You do not need to show any work here. Okay, you don't need to show any work here because it's not, there's no factoring or anything to do. So let me show you what I mean by you don't have to show any work. I still want you to write down the original problem, and I still want to see your logic. It just aren't steps like I just erased so much. So on something like this, where you have 2 plus x over 1 minus x as the limit as x approaches 1 from the left, what I'd like to see then is do a little bar, do a little that, and now you don't have to show work in that you don't have to show me physical numbers, but in your brain, you'd say, okay, well, if it's approaching 1 from the negative side, that would be like 0.9, 0.99, 0.999. So on the top, if I put in 0.9, 2 plus 0.9 is 2.9, that's positive. As I approach from here, 0.9, 0.99, that's going to be positive also. And so that would be positive infinity, or just infinity. All right, so you don't have to show me anything. You don't actually have to put in 1 minus 0.9 and 2 plus 0.9. Now, some students like to do that so they could just see it as 2.9, which is positive, and 1 minus 0.9, which is 0.1, which is positive. But you don't actually have to show me that. All right. Let's look at B. So we have the same thing, the limit as x approaches 1 from the positive half, 2 plus x over 1 minus x. And so there's an infinite discontinuity here. This is a vertical asymptote at 1. So you know it's infinity, but we don't know if it's positive infinity or negative infinity. So we just go a scooch over 1. So that was like 0.9. This is going to be like 1.1. So if I thought about it like that, that's positive 2, 3.1, right? And then this 1 minus 1.1, that's going to be negative 0.1 on the bottom. So that's going to be negative. And so a positive or a negative is negative infinity. So in fact, if I would have asked this problem without the left hand and the right hand, which is next. So the limit as x just approaches 1, no left hand or right hand, of 2 plus x over 1 minus x, the answer is it does not exist because the left hand limit and the right hand limit disagree. They do not match. One is going down forever, one's going up forever. All right. All right. Evaluate the arc cosine of negative 1/2 and the arc tangent of 1. Oh, yeah. And okay, so when I taught this, the last time I taught this, there was a very interesting question that I can address here. So there we are, limits. So again, let's make that quick little chart here. Pi over 6, pi over 4, pi over 3. Sine and cosine, and 1, 2, 3, 3, 2, 1. Divide everything by 2. And square root the numbers that aren't 1. All right. So they want the arc cosine of negative 1/2, and they want me to evaluate that. So what does that mean? That actually means they want to know what angle is equal to this. So if we said this, if we said y is equal to the arc cosine of negative 1/2, what we would do is say, oh, okay, well, we could take kind of the cosine of both sides, if you want to think of it like that. But at the end of the day, what that means is just the cosine of y is equal to negative 1/2. That's what they're after. That's what they're going for. And so when you look at the principal values, they're called the principal values, because this actually is infinite, right? If you actually think about the cosine curve, we've got an infinite set of correct answers here. Where is it negative 1/2? The cosine curve keeps, it's negative 1/2 there, and it's negative 1/2 there, and it's negative 1/2 there, and it's negative 1/2. It's negative 1/2 infinitely. There. So we could just keep going around the unit circle and finding answers where the cosine is negative 1/2. They don't want that. So what they did was they prescribed, they're called the principal values, or when you actually look at like the arc cosine curve, only give you from 0 to pi. So it's just this piece. So that limits the cosine to the first and second quadrant only. And so when they want the arc cosine of -1/2, they're talking about just Q1 and Q2. And so when we work backwards on that and we say, okay, well, when is it 1/2? The cosine is 1/2 at 60 degrees, or pi over 3. That is when it's 1/2. And so we actually don't want that one, we want this one. So when the reference angle is pi over 3, what is this angle? So that's what we want here. So y is going to equal, what is that? That is, remember this is pi, so that's like 3 pi over 3 minus pi over 3. So 2 pi over 3. And we can't, now again, the question that always came up was all-star trig class. All-star trig class. And so how do we know they didn't want this one? Why don't they want that one? The 300 degree, right? That's 60 degrees. So 60 degrees, 300 degrees. Why don't they want that one? It's because the principal values limit it to 0 to 180, 0 to pi. So we don't want that. We want this. We want 120. All right. Lovely dovely. Then the next one is the arc tangent is 1. When is the arc tangent 1? So again, arc tangent, instead of jumping through all these hoops here, we're just going to say y, the tangent of y is equal to 1. So when is that equal to 1? And again, the principal values for arc tangent are -90. Principal values for sine are -90 to 90, or negative pi over 2 to pi over 2. And so for the sine curve, it looks like this for principal values. This was the cosine curve. That's the sine curve. For the tangent, it's the same. It's negative pi over 2 to pi over 2. And so all the principal values for tangent go like so. And so they want to know when is tangent 1. So that's actually when is, remember tangent is sine over cosine. And so in the fourth or first quadrant, when are they the same? And that would be at 45 degrees, right? This over this, the square root of 2 over the square root of 2. So pi over 4 for that one, pi over 4. That would be the square root of 2 over 2 and the square root of 2 over 2. We'll give you 1. So that only happens at 45 degrees. And there we go. And again, why can't we use the fourth quadrant for that one? Because only cosine is all-star trig class. Only cosine is positive in the fourth. And so the sign would be negative. So that would actually be -1 if we did those. So the only correct answer is just 45 degrees, pi over 4. All right. Expand completely using the rules of logs. And we had to do that, right? We kind of did a nice little workaround with logs to help us do derivatives. That was kind of fun. We're going to do that again. But this one, they just want us to write out the logs. So that's just easy peasy lemon squeezy. Multiply in log land means add, and divide in log land means subtract. And you actually, that goes all the way back to, logs are just kind of a fancy way of writing exponents. And so if you think about your rules of exponents, when I had x to the 7th times x to the 5th, I took 7 plus 5 and said x to the 12th. When I had x to the 13th over x to the 3rd, I took 13 minus 3 and said x to the 10th. And so keeping that in mind, when you're in log form, ln x plus 2 cubed square root of x minus 1 over x to the 4th. So remember, we'll do a quick rewrite here. ln x plus 2 cubed x squared minus 1 to the 1/2 power over x to the 4th. So that's the same, the square root and the 1/2 power. All right, so now these are going to be positive. Those would be multiplied. That's going to be negative. That's divided. So that means like subtract. So if I write these out as logs, remember, oh, here, we'll do it in 2 steps. It is notes. Okay, so now we're not done because we can still come on down. You can pull those powers when there's a log and there's a power involved on what's going on there. You can pull that out front as a coefficient. And in the chapter 3 review, we're going to do this all in one step. All right. You should always, reminder on the test, don't leave off these parentheses. If you leave off these parentheses, you're going to lose points. You're going to lose points because this means 3 ln x plus 2, opposite. You need the parentheses on that. Here, you can omit it. Now, I've had some students go, you know what? I'm putting parentheses no matter what. Anytime I'm working with logs, I'm always putting parentheses. That's fine. It's not fine if you omit the parentheses here, because that means you're just doing the natural log of x squared and then subtracting 1. So watch those tiny little details, right? Tiny little details matter. Also, don't forget the ln. A lot of times students leave off the natural log. That's kind of important. And then what are we doing here? Solve for ln or e. Okay, so they want us to solve for x. Yeah, here, I'm going to erase the board. That's going to require a little bit of work. Not much, though. These are quick. So we've got 10a is 6 is equal to e to the x minus 2. You could kind of take the log of both sides, like do ln 6, ln e to the x minus 2. And now see, we can bring that down in front, the coefficient, because it's power. So you have ln 6 is equal to x minus 2 in parentheses times ln e. Well, ln e is 1. Because remember what that's shorthand for. This is log base e of e. Well, that's always going to be 1 because they're asking the base is e. What do I take this base to what power to get me to that? Well, since they're the same, it's 1. So that's just a 1. And then we just add the 2. And again, here, if you just told me ln 6 plus 2, that would be fine also. But this is also okay. All right. And then the last one on page 34 is ln of x plus 2 is equal to 4. So again, when we want to do this, the easiest way is just write it as an exponential. You had to do this a lot in pre-calc. So this to that power, e to the 4th power is equal to x plus 2. And then just move the 2 over. And so that's the easiest way to do that one. All right. So that is all for the practice test for chapter 1 and 2.